Okay, we left off with this small concentrated charge, very, very tiny nucleus. It is very, very attractive to any negative charge. So we have that tiny nucleus, which is why it's so reactive. We also, to identify bronzolari acids and bases, what makes a good proton donor? It has to be very electropositive. Hydrogen is already electropositive, so a good proton donor needs to be very electronegative. That is a terrible background color for that color. Awful. Even with no audience. Awful. Let's do it there. There. Much better. Much better. Much better. Okay. So if we take a look at what it does, what is going to make our hydronium and what's going to break apart that acid easily? So we have water with its attractive lone pairs. Lone pair electrons. It's a very, now it doesn't have a negative charge, but it's an area of concentrated negative charge on that side of the oxygen. If we have an acid, like say hydrogen paired with an electronegative ion like iodine versus an electronegative and even more electronegative fluorine, which one of those will be the better acid? In addition to being electronegative, we also have to look how well can it bond to the hydrogen. If it's bonding really well, it's not going to break off very easily. And so this giant bond, because iodine is a bigger atom than fluorine. It has more shells. So if you recall your atomic sizes, as you go down the periodic table, the atoms get bigger and bigger. And so this, when we have the bigger atom, oops, I should do that in a different color. This is attracted and the large distance from iodine makes that the iodine is not hanging on to the hydrogen very well. And so the hydrogen is much more likely to be able to let go and become a strong acid. Hydroiodic acid is a strong acid, whereas hydrofluoric acid is a weak acid. Even though the fluorine is more electronegative than the iodine, the size also makes a difference. So it's not just electronegative, it's electronegative plus a large size. And so this is smaller distance more tightly held to the fluorine's nucleus. And so it doesn't come off as often. It's a weak acid. We haven't fully done the difference between weak and strong acids, but in a strong acid, all of the hydrogen is removed from every species in solution, whereas for weak acids, it will exist in an equilibrium, only some of them removed, and later on we'll talk about the equilibrium. And so what makes a good acid, a strong acid, is number one, the partner needs to be electronegative, and as well, it also needs to have a long-distance relationship. As you go off into your graduation and attend university next year, you'll be able to see all your friends who are together, who go to different universities, slowly break up over the first 2 months if they don't visit each other and renew that connection. Long-distance reactions don't work very well. So, bigger atom has a greater bond length and therefore makes a better proton donor. So, first criteria was electronegativity. Second criteria was how big it was. So big. So hydrochloric acid, strong acid. Chlorine. Hydrofluoric acid, weak. Hydroiodic acid, strong acid, even bigger. Strong, weak. And fluorine is more electronegative than the other two. Proton acceptors. Now we're getting into the base. What makes a good base, particularly a Bronsted-Lowry base, one in which you're not giving off hydroxide? One way you want to attract those one way you want to attract those hydrogens is have lone pairs of electrons. If you have lone pairs, then there's something for it to attach to. The most famous version that we use in class, of course, is ammonia, because ammonia, I don't like that color. Let's use, ammonia's green. In my head, ammonia's green. You've got this nitrogen to hydrogen, and you have that lone pair right there, and that makes it very attractive to hydrogen. So if you have hydrogen, it's going to see that, and it's going to react with it. So let's take our ammonia. React with hydrochloric acid. You'll get and this whole thing becomes +1. There's a variety of organic structures. This is a pyridine, and you'll have in DNA and in amino acids. The amino part is a base, because they all have nitrogen. Having a lone pair is a very common thing for hydrogen to have, and they often can function so they can bond to hydrogen and act as bases. So if you have lone pairs of electrons, you become very attractive to hydrogen that's looking for any negative charge it can find to bond to, because it has that very, very attractive, concentrated, positive charge. Now, how could you be even more attractive? Well, if you have a lone pair of electron, you have an area that hydrogen is going to be attracted to. So you have a bonding location. It can take those two electrons and you can form a bond with it, a covalent bond. But what else could you have? Well, you could also be negative. Negative is like, not only do you have an attachment point, an area in which you can bond, but you also can show that you have lots of wealth. You have a good job, high paying, lots of cash. You can attract all sorts of hydrogen partners. So have a negative charge. So the classic base is hydroxide. And why do we define bases by how good hydroxide was? Because it has 3 lone pairs and a -1 charge. Hydrogen's going to walk by that and say, woo, I can't give that up. I can bond to any one of those and essentially become water. And I've got that negative charge to track me over there. If I have CO3 -2, I've got carbon double bonded to oxygen, bonded to oxygen, bonded to oxygen. Badly written. And so we end up having a lot of lone pairs, plus the whole thing has a -2 charge. Hydrogen's like, sweet. Look at all those bonding positions that I can be attracted to. Look at that negative charge. In fact, I am going to be attracted twice, because CO3 can react and take 2 hydrogens, become H2CO3. So it can be twice as strong as a base because it's got multiple attachment points. Now, next day I'm going to ask you to draw some things. As you may have noticed, knowing the Lewis dot diagram is handy for discussing this. I'm not going to directly test you on drawing Lewis dot diagrams, but you are going to be able, you are going to need to be able to draw them. So next day I'm going to ask you to show me how you come up with the Lewis dot diagrams of those, and I'll probably add a couple more that I'm not putting here. This will be after the test, though. Just make sure you know how to do that. Next up, what isn't a base? Well, alcohols aren't bases. They look like they are because they have hydroxide. But this is an alcohol, ethanol, also known as drinking alcohol. It does have lone pairs there. It's not a base. It's also not an acid. That hydrogen doesn't pop off. It stays there. That's a really strong attachment point. Now, the oxygen is electronegative. It's not. It's next to fluorine. Fluorine is electronegative enough that if you have HF, you've probably got an acid there maybe. But with oxygen in this particular configuration, it's not quite electronegative enough to pull the electrons away to allow the hydrogen to go away. And this bond's not going to break. That is way too strong. There's nothing weakening that particular bond. So that is just an alcohol group. Alcohol groups are not hydroxides. They do not break. It is not an electrolyte. It's not an electrolyte. There are no ions here. That oxygen is less electronegative than chlorine. It's not enough to release the hydrogen, so it can't be an acid. So it's not usually an acid. In fact, an acid would be slightly more likely. I mean, you can force it in areas of chemistry we're not going to cover. But it's slightly more likely. Breaking this bond, though, not going to happen. Definitely not a base. So this is just nutrimolecular. You don't have to worry about acids and bases when you're dealing with alcohol. You just have to worry about being poisoned. So not usually an acid. However, this structure you will have seen in your biology classes. That's an R group. It could be anything. If we were doing an amino acid, which I'll draw below, that would be attached to something. This is known as an organic acid or a carboxylic acid. A carboxylic acid or an organic acid has the structure. So before, this couldn't break and that couldn't break. So we've got a little bond there. That's not breaking. This isn't breaking. But we have this new oxygen here. That oxygen is electronegative. This oxygen is electronegative. So these guys are both electronegative. They're both electron suckers. So they're there trying to steal all the electrons from everybody. So first of all, that oxygen is stealing the electrons from that carbon, just pulling them in this barn. And this carbon, not a happy camper. It likes its electrons. It's sort of middle of the road between electronegative and electropositive. So oxygen can steal it, but it's not happy. So it's like, oh, fine, you take some from me. I'm going to take some from you. And it pulls away some electrons from that oxygen. And so the electrons move this way. That oxygen is electronegative. It's not happy, and so it moves the electrons out of here. This bond right in there weakens and breaks. Now, it is a weak acid. It's not going to break every single time. It'll exist in some kind of equilibrium. However, it does it often enough. This is how acetic acid or vinegar is an acid. That you get R, C double bond O. Again, carbon to oxygen doesn't break. Carbon to oxygen doesn't break. But that oxygen does keep all of its electrons, not going to take my electrons from me, and that hydrogen just pops off. So if we look, this plays a lot of roles in biological chemistry. Biochemistry is fantastic for this. Probably put that there so you can write it down. But you've been told about amino acids. They're enzymes. They do magic. Okay, next one. These are the types of acids and bases that we now do in Chemistry 12. We're going to look at acid-base pairs. Oh, when I ran out of the room, I dropped my notes. So, these are conjugate. Conjugate acid-base pairs, and every Bronsted-Lowry Bronsted-Lowry. So that's the new type of acid bases that is defined on protein donors and proton acceptors. In every Bronsted-Lowry reaction, there is an acid-base pair. So for example, here we have our organic acid, which in this case is our base. Our base is water. Water can be a base. It's going to accept a proton. So we get CH3, COO minus, plus H3. Yeah, that's a terrible 3. And now we have a base. And of course, H3O plus we know is pure acid. So we have these in pairs. This acid with that base is a Bronsted-Lowry acid-base pair. This water is acting as a base with that H3O plus as an acid. That is a Bronsted-Lowry acid-base pair. Conjugate acid-base pairs, a pair of chemicals which differ by a proton. And that says proton. So, I would like you to write out the reactions that occur between these acid-base pairs and identify the conjugate acid-base pairs. So we have NH3 plus H2O goes to HNO2 plus F minus goes to H CH3 COO plus SO4 minus 2 goes to HCO3 plus, I would have a negative charge there, S minus 2 goes to, and last, but certainly not least, HSO4 minus plus HSO3 minus goes to. Now, this one's a trick, this last one, and if I was there, I'd explain why it was a trick after someone did it incorrectly. But I am just going to give it away and say, treat that one as the acid in this particular case, and it'll work out, and I'll explain it why when I'm back. I'll do the first one. NH3 plus H2O. We know that NH3 is a base. I've mentioned it numerous times. So this must be the base. That means that's the acid. The acid is the proton donor. So that becomes NH4 plus OH minus. That means if we were to reverse the reaction, this would be our acid, and that would be our base, which makes sense. Hydroxide is a base. To identify our acid-base pairs, NH3, that is a Bronsted-Lowry acid-base pair, and this is a Bronsted-Lowry acid-base pair, and we can identify them on this side as NH3, NH4 plus, and H2O and OH minus. Let's see, NH3 is base. For each one of these, write out the reactions on each case and identify the acid-base pairs as I did for the first one. There are some definitions I'm going to whip down and do right now, so you can start on that in a moment. The definitions I'm going to do down here at the bottom is you may have just noticed that water acted as both an acid and a base in a couple of reactions. Water is known as amphiprotic. That's an M. It can act as both a proton donor and acceptor. Water being amphiprotic, it can react with both an acid and a base because it can be both an acid and a base. It has twice the chance of a date on a Saturday night. It must be able to lose a hydrogen. So if you're going to be amphiprotic, you have to have a hydrogen, but they're often negatively charged. So they often have this format, HX minus. They have a negative charge to attract a hydrogen, but they also have a hydrogen to give away. Our examples would be H2BO3 minus, HCO3 minus, HPO4 minus 2, HC2O4 minus, and some of you may have guessed, oh, where is HSO4 minus? And the answer to that is no. HSO4 minus cannot be amphiprotic. There is no exception, no place in which it can. It's an exception to the rule that I will probably explain later. But if I was to pick one of these, you can then get a reaction like, let's take this one, and let's write in a different color, HPO4 minus 2 plus H2O, HPO4 minus 2 plus H2O. Water's doing it in both times, so these are both acting as amphiprotic. Is that HPO4 minus 2 can act as a proton donor and become PO4 minus 3 plus H3O plus, and it made acid. Or it can accept a proton and become H2PO4 minus 1 and make hydroxide. It can do either one. Now, it's one of those is preferred in water, but it means if it's with an acid, it can be a base, and if it's with a base, it can be an acid. In addition, we have things monoprotic, diprotic, and triprotic. That means monoprotic means it has one hydrogen, like hydrogen fluoride, or hydrogen chloride, or hydrogen bromide. Diprotic means it has two protons, like H2SO4. Can't see green on green very well. H2SO4. And triproduct is like H3PO4. It has three protons. Let's see. I think there's one last definition. Conjugate acid, substance that has the proton. And conjugate base, the substance that lacks the proton, so it can accept it. In conjugate Barnstad-Lowry acid-base pairs, there are two conjugate acid-base pairs. You need an acid to react with a base, and that base needs an acid to react with, and then they become their opposites. So, for example, if you have let's do our substance that lacks the proton, PO4 minus 3, since we just did that, plus HSO4. there's our proton donor. We are going to get PO4 minus 2 because the hydrogen is going to add to that. So that makes this our base and this our acid. And then the other one is going to act as the proton donor, so it's going to make SO4 minus 2. And so that makes this one the acid, and that becomes the base for the reverse reaction. So in every Bronsted-Lowry reaction, there are 2 conjugate acid-base pairs because, as we have just seen and done, there's a base and its conjugate acid. There's an acid and its conjugate base. 2 pairs. And I think that's more than enough for speed learning. What's the next thing? What? That's exactly what I did here. Nonsense. Should have deleted the other page. Anyway, ignore those. That's the other page. We will continue with this part, right balance equations, next day. I think that's enough notes for a Saturday. Go back and do these reactions, writing out the 2 acid-base pairs for each one and predicting the products. And I'll see if I can cut out some of the dead air in the middle later on if I have time, but if I don't, you have the ability to have fast forward, and I hope you did so.